Alright guys, welcome back for another video, and in this video we're going to take a look at data augmentation. So what we have here are just some basic imports for TensorFlow and Keras, and then TensorFlow datasets as TFDS that we looked at in the previous video. And so we're just doing pretty much the same thing as in that video. We're loading the Cypher10 dataset. And then so this is pretty much copied from the previous video. We're doing some normalization of the image. So we're dividing by 255. And so we're mapping every image through this normalized image. We're doing cache, shuffle, batch, and then prefetch. And then pretty much the same on the test set, except we don't have cache and shuffle. And then we have some model that is pretty simple. We take 32 by 32 and 3 channels as input. And the first layer is just so it's a very, very small model because this is just to focus on the data augmentation part. But essentially we have 2 conv layers, max pool, conv, flatten, and then 2 dense layers at the end. And then model compile and model fit for 5 epochs, and then model evaluate. All right, so what I want to show you are 2 ways to do data augmentation. And so the first one of these assumes that you're working with a TensorFlow dataset. That is going to be the case most of the time. Either you're loading through TensorFlow datasets or you're doing custom data loading for your custom dataset, which we haven't covered yet, but we will in future videos. And so what we're going to do here is we're going to define another function. We're going to define another function right here. Define augment. And then we're going to send in image and label. And there are a bunch of different TensorFlow functions that you can use for data augmentation. And I will link to the documentation that you can go through all of them. I'm just going to show you sort of the structure of it and some basic ones. And then, of course, you can add more if you like or remove some of them. But so let's say, first of all, we want to sort of resize the image. That's a common thing. In this case, the images are already resized to 32 by 32. But maybe sometimes the image isn't exactly, maybe not all of the images are exactly that size. So we might need to do some resizing. So what we're going to do is we're going to do new height equals new width, and we're going to specify it as 32. So we're not going to do any resizing because it's already done, but just how you would do it. So image is then equal to tf.image.resize. We're going to send in that image, and then we're going to specify the new height and the new width. All right. Then let's say that we want to, convert the image to grayscale. So the channels now are 3 channels, right? Let's say we want to convert it to grayscale so that our model can do predictions on grayscale images as well as colored images. But perhaps we don't want to do grayscale on all of the images, right? We want to still have some color. So with some probability, we want to convert it. Then you could do something like if tf.random.uniform, and you could specify the min val, say 0, max val 1. Let's say if that is less than 0.1, all right, which will happen in 10% of the cases, then what we're going to do is we're going to do tf.image.rgb to grayscale of that image. Now, one issue here is that since we're converting to grayscale, the out channel is just going to be 1. But of course, our model in this case is going to expect an input channel of 3. So one way to solve this is that you can copy that one channel across the 3. So you can copy that one channel to become 3 channels, except that all of those 3 will be identical. But that's just so that the model will actually work. So you could do something like tf tile. And then you could do 1, 1, 3. So essentially here we're going to not copy this dimension, not copy this dimension. And here we're going to copy it 3 times. And this is the channel for this is the dimension for the number of channels. This might be a little bit tricky. So if you don't completely understand it, that's okay. Just make sure that you check out what this tf.tile does. And then just really the point here is that you can use if statements and stuff like that and not have a deterministic augmentation of your examples. So you can introduce randomness into your data augmentation. And I guess one thing that's really important to say here is that I oftentimes see people talk about data augmentation like you're sort of expanding your data set so that if you have 100 images, with this data augmentation, you're going to get 300 or something like that. And that's not really how data augmentation is done. Normally, how you do it is that you do it on the fly, so that this is done sort of on the CPU in parallel while the GPU is training the model. So while it's training the current batch, it's fetching the next batch and it's doing the augmentation in real time on those images. And so sort of you're effectively making your data set larger, but it's not really. So for example, if you just take a look at this one, where for each image, we're with a 10% probability, we're making it grayscale. What is the effective data set size when we've introduced this data augmentation? It's kind of tricky to say, and especially if you introduce more randomness. So let's say, for example, we do image equals tf.image.random brightness of image, and then we specify some max delta in the range of how much it can change the brightness. So what is the effective data set size after we introduce something like this, when we introduce some random brightness to the image? Well, I guess infinite, because it could change the brightness of the model just slightly, just very, very slightly on a specific pixel. And it can do this on every image. So I think that way, talking about the size of the data set after the augmentation is a little bit tricky. And so just keep that in mind. And one more thing is that all of these are going to be done on each image, and it's going to be done in sequence. So first we're resizing, then we're doing the random RGB, random RGB to grayscale. Then we're doing the random brightness. Then we could add more stuff. And again, I really encourage you to look out the documentation, because there are tons of more, and you can also create your own sort of data augmentation. In this case, we're just using their functions, which is good enough for most cases. So we're just going to do tf image.random contrast. We're going to send in the image. We're going to specify some lower value and then some upper value. And what exactly these functions are doing, I guess you can sort of print them and see what it does, but exactly what they do, I would read what the documentation for these specific functions. So this, I guess, in this video, we're learning how to use data augmentation, not really to implement it from scratch. And so one more thing also is that a very common data augmentation is you can flip the image vertically or horizontally. Although I would be careful, sort of depending on the data set you have. So let's say you're using MNIST. You wouldn't want to flip images horizontally, for example. Because, for example, if you vertically and horizontally flip a 9, that would inherently change the digit of the image, right? So you want to make sure here that the data augmentation you're doing isn't actually destroying the correct label for the image. So just be careful with data augmentation. More data augmentation is not always better, and you need to make sure that everything you do just still maintains the correct label for every image. But I mean, let's say you have pictures of dogs or something. Then if you horizontally flip a dog, that's still a dog. So, or if you vertically flip it, it's still a dog. So in many cases, it makes sense. Just be careful with it. So then we're going to do image is tf.image.random flip left right of image. And this is going to, in 50% of the cases, randomly flip it left and right. I would want it to sort of, that you could choose the probability of flipping. I haven't found a function that can do that yet. I guess it's not too difficult to implement yourself, but it's available through PyTorch. So I think TensorFlow could do it as well, and hopefully they do in the future. And then you could also do image, TF image, random flip up down of image. I'm not going to, with 50% probability again, I'm not going to use it in this video though. And then at the end, we're just going to return image comma label. All right. So now that we have our function here, what we're going to do is we're going to map it. So for example, we're going to do it after the shuffle here. We can do dstrain equals dstrain.map and then augment. So it's going to first normalize the image. And I guess we could also specify num parallel calls. Since there's nothing inherently, for each image, this can be done in parallel. So that's why we do this num parallel calls. And yeah, so I think that's it. That's really all we need to add. So let's just run it first of all to make sure that it actually works and so on. All right, so it does seem to run. And again, we're not looking for performance, although I would highly encourage you to sort of, in previous videos, we've trained on Cypher 10, and I think we got, I don't know, like 78% on the test set or something like that. And introducing data augmentation, I think you can do a lot better. And with some model modifications, I think you can do at least get it up to 90%. So that's one thing I highly encourage you to do. Just play around with the code, add data augmentation, see if you can improve the accuracy. And do let me know how it goes for you. But so this is one way to do data augmentation. I'm going to show you one other way. And sort of this is the way that I think is recommended. This is highly efficient and it's done while your model is training. But another way that's common is that you could do, and this is for TensorFlow greater or equal to 2.3.0, which is the latest version as of right now. And so what we can do is we can do data augmentation and we can do a sequential model. So essentially here, we're going to add data augmentation as part of our model. And I think there are pros and cons of this. I think it's more simple because it's just part of your model. And but I'm not entirely sure if that is actually done while the model is training. So for example, for the data augmentation we did here, this is done in parallel while the model is still training on the current batch. And this is done on the CPU at the same time, so to speak. And I think so you lose some performance doing it this way, but I think it's I guess more simple. And anyways, we're going to do layers.experimental.preprocessing. So it's in the experimental branch. So as you can see, it's this is still new. That's why it's only available in the latest model. And so we're going to do preprocessing.resizing. We're going to specify height and width. And again, I'm going to link to the documentation of this experimental preprocessing. There are a lot of different functions here. But you could do layers.experimental.preprocessing.random flip. And then you can specify a mode. And you can specify the mode to be horizontal and vertical, or just horizontal. So to keep the same data augmentation as we did previously, I'm just going to do horizontal flip. Then we can also do something like layers.experimental.preprocessing.random contrast. And then we specify a factor, let's say 0.1. And yeah, that's it. So you can add more, of course, you can add a lot more. And but I think that's fine just for now. And then what we're going to do is we're going to add it at the top here. So we're going to do data augmentation right here. So it's going to run through the data augmentation, and then it's going to be sent through the layers. And so let's just run this and make sure that it works as usual. Wow, that was a blunder. I accidentally stopped the recording, and I think I spoke for about 10 minutes. So I'll just try to remember what I said. So I think, so what you can see here is that we got 41% after just one epoch. And if you, and again, we don't care about the accuracy here, but if you would compare it to what we did previously, I think we just had 26 or 28% after 1 to 2 epochs. And I guess we're using the same model, right? The only thing that differs is the data augmentation. So previously we used some more data augmentation in that we had this random brightness and we also had this random grayscale. And so when we add more data augmentation, we're making it more difficult for the model to overfit or to the training data because it's seeing such huge variety of images. So in previous videos, we've talked about regularization in terms of L2 and dropout. And one really powerful method is data augmentation. So essentially, overfitting is adapting too much to training data, right? It's just one sort of interpretation of overfitting is that it essentially just memorized the training data, and memorizing doesn't lead to generalized understanding. And so sort of one thing you can do is that if you just think about it from your own perspective, having more stuff to memorize makes it harder, right? If you have very few things to memorize, it's very easy to just memorize them. And it's the same thing for the network. So if we're adding more stuff, if we're adding more images, it makes it harder for it to memorize them, which reduces overfitting. So in addition to these L2 and dropout, I highly encourage you to try out data augmentation, not only for expanding the data set so that the model improves, sort of the performance of the model is going to improve as well because of having these more images to train on, but it's also going to reduce overfitting. And so, yeah, I think that's it. If you have any questions, then leave them in the comment section below. Thank you so much for watching the video, and I hope to see you in the next one.